music beat, feel it properly. People of the world, do it properly. Wherever you are, you're a superstar. House music is the thing that brings us together as one. So together, we're gonna do this thing properly. Let's have some fun. Party people, jump, 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 jump. Do it properly. Let's have some fun. Do it properly. If you're feeling the beat over there, do it. Put your hands up in the air. Do it properly.
Check this out.
There's so many ways to do it. So many ways to see.
All right.
But the only way to do it is to do it properly.
All right. I think we are live now. Well, I know we're live. I think we can hear me on the vocals. All right. Hello, everyone. My name is Verde Robusto. This is the Schumann Resonance channel on Facebook and on YouTube and points beyond. All right. So, thank you all for being here. This is the Schumann Resonance Harmonics channel on YouTube and on Facebook. Thank you all for being here. If you are new here, welcome, and thank you for showing up. It is what's today? Tuesday, Wednesday. It's the day before Christmas. Thursday. It's Thursday already. And it was a little chilly. I haven't been outside in about 2 days. I haven't had to work. I haven't really gone anywhere. My bike is downstairs here in the basement, so it's not getting rained on. And I'm getting a high. I'm just looking at the meter here, and it's pegging it out for some reason. All right, so it's not been too rainy out. It's not been too bad out. It is winter time. It is Christmas time here, but it's generally speaking, it's we're in doing pretty well here. We don't have a lot of snow, and the sun's activity has been fairly quiet. A lot of people get a lot of stuff. I don't even know what to call it. Excitement. A lot of energy comes from the sun, and it affects us in varying ways. And people get an active. I don't even know what to call it. People get activated through the sun, and then there's a lot of excitement in their life while we are assimilating the solar energies coming in. So relative to me, that's been quiet. There's not much going on. All right, that's a long way of saying that things have been fairly stable for me here. For anyone who is wondering. All right. Okay, so let's see. Almost 5 minutes into it, let's get into the program. So, all right. So, as usual, there's some introductions I do to kind of get into the material. And one of those introductions is the music. I've already gone through the music. Hold on. Back. Okay. So I tend to do a little bit of an introduction. When I do these, I want to try and kind of get into them, methodically and do some background first. I need, in a lot of cases, I sort of have an introduction that I do, to get into a disclaimer. I'll just put it that way. A lot of times I have disclaimers that I do, especially if I'm talking about the ringing in the ears and stuff like that I'm not a medical doctor. All right, so this is one of the disclaimers. Okay, in this case, on this lesson here, we're talking about the Schumann resonances relating to the modes. Okay, so I'm talking about the coloration of the Schumann resonance charts and graphs. What are they? That's the basic premise of what I'm answering here is what's up with the coloration on the Schumann resonances. Okay, you can't really, a person, in my view, person can't look at the colorations on the Schumann resonances, start making stuff up and saying it's this and that without understanding properly what the modes are, how they measure these things, and what the colors represent. Because the colors of the Schumann resonance charts are not like you in an abstract painting in art class that you just have a palette of colors and you're going to mix them together to see what they look like. All right, that's not what the Schumann resonances are. It's not like open for interpretation like a Picasso painting, for example. All right. This is photorealism. This is happening right now on the spot, and this is a documentation of the Schumann resonances, are a documentation of what's happening around the globe with the electromagnetic frequencies. All right. So I use the phrase when I'm talking about the Schumann resonances, I'm talking about the plotting of the material. I talk about this from the perspective of if you were doing a painting. That's an analogy I'm making for people to get an understanding of what the Schumann resonances are, that you are starting with a blank canvas, and upon that canvas, you're putting the information, the photorealistic information of what's happening around the globe and in your neck of the woods. Once again, as a general rule of thumb when dealing with the Schumann resonances is know the difference between what's happening locally and with what's happening around the world. All right. And so depending on where you are geographically on the world, what's happening with you locally may not be what's happening over in Russia at the Tomsk SOS Observatory. All right, so that's important to note as well that when we talk about the action and the behavior of the Schumann resonances, what it's doing on the graphs, it's important to know the difference between local interference and what's happening on the worldwide stage, if you will. Okay. Okay, so with those disclaimers made, I think let's get on to the material. And what I'm going to do is I think give you, as I usually do, give a basic description of what you're looking at here on the screen on my thumbnail. Okay, so it says, what are the colors of the Schumann resonances represent? It's the modes. In Tomsk, Russia, our four primary colors are white, yellow, green. I'm sorry, white, yellow, red, and green. Excuse me. Each color represents a mode. Mode colors are white equals 1, yellow equals 2, red equals 3, green equals 4. We see these numbers on the graph strips coming from Tomsk, A1, A2, A3, A4, etc. What does this code mean? Okay. In a nutshell, the A1, A2, A3, A4 is amplitude mode 1, amplitude 2, amplitude mode 3, amplitude mode 4. Q is quality mode 1, quality mode 2, quality 3, quality 4. F is frequency 1, frequency 2, frequency 3, frequency 4. Let me find an illustration of the Schumann resonances so I can show you. Okay, this is the most recent image of the Schumann resonance harmonics graph. This is the one coming from Russia, Tomsk. And so what you're seeing on the screen is, as I was showing you, A1, A2, A3, and A4. Okay, this chart is amplitude. So first off, this is the spectrogram. Okay, so this right here, the top one, is a composite of everything below it. All right, so this top one is the dependencies of amplitude, dependencies of quality, dependencies of frequency. All right, so all of that is contained here in this one spectrogram. The top view is the composite of the ones below it. All right, so amplitude is A1, A2, A3, and A4. That's the electric portion. Okay, quality is this right here, Q1, Q2, Q3, Q4. This is quality. This is the magnetics portion. Okay, and this one down here, the fourth one is frequency. This is F1, F2, F3, F4. Okay. All right. So when we talk about the codes, the letter codes, we're talking about amplitude, quality, and frequency. Okay. So so within those dependencies, there are different ways to measure it. Okay. Let me go back to my teaching model. Hold, please. Okay. So you have seen the place where on the Schumann charts you see A1 to A4, Q1 to Q4, F1 to F4. Okay. The best way to look at or see these modes relative to our canvas or the painting analogy is to see the modes as different size and shape instruments, which we'll get into. If you're familiar with brushes or calligraphy pens, and you know the nibs come in different sizes, different shapes, we're doing different types of writing and different types of work, then you will have a basic idea of what we're understanding. The theoretical painting is photorealism. We are representing actual events in real time as they occur. This is called plotting. The amplitude is the height. The magnetic strength and direction or quality of the incoming signals is plotted using the tools of these mode to draft a spectrogram of the signal. All right. So in order to give you an accurate representation of what the signals, what's coming in, you have four colors with Thomson, 4 colors in addition to the background of the blue. So you have 5 colors, essentially 5 colors that you're using as the primary tools to create the spectrogram, which is, oh, hello. All right, so this is the, so again, the tools of the 4 brush shapes and sizes of amplitude, 4 brush shapes and sizes of quality, 4 brush shapes and sizes of frequency. Hopefully you're staying with me. Hopefully you understand how I just got the analogy of the paint brushes and the tools of what we're talking about of the painting. Hopefully I haven't confused you. Okay. But this, like I said, it's difficult to give people an understanding of what the Schumann resonance modes are in a logical way of just the words. I have lots of definitions, lots of words of how to explain it to you, and it means nothing. I assure you, just giving you the definition of what the modes mean will not help clarify it in any way. So I need to give you pictures for you to understand when I'm talking about a canvas, and I'm talking about the tools that you use to make a painting of the spectrogram. The best way to understand this is, if you're new, the best way to understand this is through an analogy of a painting or drawing or some pursuit where you actually yourself can use a tool or a paintbrush and create a product, a painting. If you've never painted in your life, if you've never drawn anything in your life, if you've never used a crayon in your life, this is going to be a long, disastrous road to try and explain what the Schumann resonance modes are to you. I have a lot of words again. There's a lot of words that I can use to describe this, and I'm happy to throw more words at it, but you really need to get a picture of what we're talking about. And that's where the analogy of a painting and the creating a portrait, preparing your canvas, getting your array of tools and your brushes and your paintings out, and the colors rather in the painting. This is what the best description for the modes of the Schumann resonances are, is to allow you to understand the painting analogy that goes into this. Okay. So with that said, let me get on to my my material. One of the most common questions I get that people ask is, what do the colors of the Schumann graphs represent? Okay. So this video is in reference to that answering that question. What do the colors of the Schumann graph represent? All right. So a disclaimer, I guess, or a some introductory remarks. Let me narrow this field. There are multiplications around the world which measure the Schumann resonances. Each institution which measures and publishes their results does so in a manner unique to their own methods of data collection. Some sites use a Marconi-type antenna, which measures the amplitude or the electric portion. Some sites measure up to 120 hertz. Some stop at only 50 hertz, like the Ukrainian station. Based upon the hardware being used, in addition to the software suite which analyzes the signal, the result will be plotted. The resultant report gets plotted accordingly. So, depending on what their method of collecting a signal is, and how their software plots it out to the spectrogram, you'll get a lot of different results. There's similarities between them, and it's good to know the similarities, but it's also good to know the differences, meaning how they truncate or what the filters stop the signal at. So in many cases, there's a 50 hertz filter that filters out 50 hertz because of the commercial power grid. So it's important to know if you are using a station, or if you're looking at a station that truncates at 50 hertz on the 50 50 hertz on the resonance scale. All right. They're also measuring in the decibels, and the decibels show up on the hertz scale, but that's a different measurement that you're getting, and that's important to know what a decibel of power rating is. And I will go into that um, later, I think, or maybe there's a different. I'm not sure where and when I'm going to go into decibels specifically, but I have talked about decibels, the power rating of decibels, and not a hertz rating. Hertz is a cycle per second. So the electric amplitude portion is measured in decibels, which is a power rating, and not hertz. But they don't have that third dimension that they can kind of bump it out in. So a lot of times the peaks, the spikes and peaks will appear as hertz ratings, and they're not properly hertz. They are actually a decibel rating that is appearing as a hertz. That's something that also is important to know. Is that the spike an actual frequency, or is it an intensity? Okay. So by knowing how the place that you're getting the information from plots the signal, it can help you decode what you're looking at. There is not one single remedy of the color solution where, for example, white equals 5D gamma energies. That's in quotes. You see, that's this phrase. It's a buzzword phrase. 5D gamma energies. It's almost in itself a code that really means nothing. How do I say this? Relative to the Schumann resonances, the antennas are not picking up gamma rays. Right? The Schumann Schumann resonance antennas are only picking up the lowest of the low, and not gamma, not X-ray, not gamma, not even optical light. Optical light is further down the track than the radio frequencies of the Schumann resonances. The colors of the reports are based upon arbitrary settings which have been introduced by the engineers of the graphs. Because of the arbitrary nature of the coloring, this here, okay, Because of the arbitrary nature of the coloring, we need to look at each graph separately based on its own color code. What is generally provided that is generally provided somewhere close to the source that you're getting this information from. Or I should say, the decibel and intensity rating will be found usually somewhere near the chart, so you have an idea on a spectrogram what the color actually represents. Okay, and I like to look at the decibel rating as almost a temperature rating or like a Kelvin scale. It's not exactly, but it's a good way to look at it. If you're going to compare it to a temperature, the color to a temperature, um, there's sometimes there's a correlation. I can't always speak on that, but sometimes there's a correlation between the color that's represented on the decibel meter, and I'm talking about something I don't have an image up to show you right now. All right. Therefore, due to the high variety and discrepancy in the variety of coloration, we're going to look at the case of two separate graphs according to two recording systems, the one at Tomsk in Russia and the other at Cumiana in Italy. All right. So let me, okay, I have up on the board, let me, there we go. All right, so I have on the board a comparison of the two different charts that we have, one from Tomsk, this is Russia, and this one here is from Italy. This is Cumiana, and this is the Russian site. All right. So one of the things that we're looking at are, the differences and the similarities. Like I said, it's important to know both. Why can't we all just be one? Because we're not all on the same page, and people have limitations, right? And that's what this is talking about. What are the limitations? Not of the Schumann resonances. What are the limitations of the ability to measure this? This is what we're talking about. Where are the parameters? Where do they stop? Where is it filtered out? Where is it truncated out? And what they're presenting. Okay. So we have two. Uh, two samples here, two charts to look at. Let us look at our charts. Okay, so the first thing that we're looking at are the spectrograms. All right, so this right here is the spectrogram for the last 48 hours. This one here on the right-hand side is the spectrogram for the last 24 hours. All right. So, and in fact, this is even a little bit more than 48 hours. It's closer to like 52 hours, I think, the one from Tomsk. All right. So what we're looking at the two of them, we're looking to compare things that are the same. All right. So one of the things that we're looking at is the background of the canvas itself. Okay, what we're using as a zero state is dark blue. You can see there dark blue, almost black, and you see here dark blue, almost black, a navy blue. Okay, this is the at-rest state of the environment. So everything that's being plotted on that is plotted onto a dark surface. So if there's any action that is there, it'll show up as a lighter shade of blue, or maybe a variant of blue like an aqua, a teal, even a green color, depending on where you're getting, depending on what the signal is, you're going toward a color. Okay. Now this, like I said, the dark blue state is the at-rest state of the chart itself. Okay. We have vertical lines that are going across here. We have vertical lines that are going across here. We have spikes that are going up this way. There's not many. And on this chart, there's not many spikes going up here vertically. Hello. There's spikes here. You notice that there's spikes here, not as many on this side. Okay. All right. So let me. It's technology. Hold on. Okay. All right. So first we'll start with our canvas. Okay. Which is okay. It's important when we're talking about the Schumann resonances. I describe this as a canvas. There's other ways. There's other more complicated words I can use to describe what this is. But the canvas, the dark blue at rest state of the environment, is our canvas. That's a prepared canvas we're getting ready to paint on. Okay. If you've never painted on anything, if you don't know what painting is, if you're not familiar with a paintbrush, if you're not familiar with the canvas, if you have no idea about painting or anything of this, and that's complicated to you, I can't make it more simple than that. All right, I'm not a miracle worker. I can only give out analogies. I do the best I can, but at a certain point, maybe this is just simply beyond people. That's possible. I try to keep this as clear and simple as I can, but when I get into down lower into the word definition of what a mode is, if you haven't understood the canvas and the size and the shape of the brushes to create a painting, to create a picture here, when I get into the word part, the word part, it's going to you're going to be completely lost. Okay. So the best analogy I can give to a person is the idea of a at rest state canvas of the dark blue, which the Schumann resonances and a lot of these spectrograms start with a very dark color, say a dark blue. It's usually, the thing, because it's a good way to mark when something has happened. You see it's no longer that deep dark blue. All right, so that's why it starts out. The canvas starts out as being a dark blue color, is because you can tell, going from there, if it's almost black, you can't add anything to it. You can't add to black. It's just all it. So what you're doing is you're detracting, you're taking away from the black and making it the black, what I'm calling black, the dark blue, taking away from it would be to lighten up the blue into a light blue or a robin's egg or an aqua color. All right. So the canvas is the background upon which the reporting activity commences. So the dark blue canvas is the background. Everything gets put upon that. Starts out with the dark blue background. Okay, this is familiar territory with most spectrograms. On the Schumann resonances, there's spectrograms and all kinds of stuff, but relative to the Schumann resonances, the dark blue is the most common background material they use. All right. It's an excellent representation of a statistical normal state, or the at rest, which is considered to be like an elastic, if you will. The atmosphere is under a pressure of type. So it's it's interactive, and it's always responding in some way to the forces around it. So this is one of the things that the Schumann resonances are showing you, are the forces interacting with that elastic of the environment. All right, hold on.